A very big hello to all my dear students. So today we are going to start with optics. After the end of the session, I promise you won't be having any phobias regarding this topic and it will be very interesting for you all. It will become your favorite topic. Let's see. Okay, so we start with what are we going to discuss in this chapter today? So we'll be talking about the following things: visual perceptions and visual acuity. We are going to talk about what are Purkinje images, what are the type of fundoscopy. We are also going to talk about visual angles, alpha and kappa. What are the different types of refractive errors? What are different types of refractive surgeries? And of course, retinoscopy, which is very, very important topic. We'll also talk about amblyopia and binocular single vision. So this is just an overview of what we're going to discuss in this chapter. So let's start. So we start first with visual perceptions. जब हम बात करते हैं visual perceptions, what are the four senses in your eyes? One is your light sense. Then second, one is light sense. Then we talk about form sense. Third is your color sense and contrast sense, right? So what are these? One by one we are going to take it. So when you say light sense, what do you mean by that? When the patient has a light sense, it means when he can differentiate between day and night, right? Whether there is any light or not, that is his light sense. Okay, so the light sense can be mainly described as perception of light, PL and PR. We should know what is PL and what is PR. So this is PL means perception of light. Okay, so PL is perception of light. So when you say perception of light, we describe it as PL either positive or negative. Okay, so either it is positive or it is negative. This is how we describe. And second, what is the second one is PR. Okay, PR here is projection of rays, not per rectum. Okay, so when you say PR, this is how we generally depict it. Ignore the boxes, we don't make boxes here. But PR is projection of rays. Samjho usko, what is projection of rays? So first thing when the patient is in front of me, suppose his vision is so less that finally I have to test his PL and PR. How do I do it? PL, of course, I will ask whether he can perceive any torchlight, whether the light is on, off, and so on. PR is you have to ask him about from which direction the light is coming. So if this is the torchlight, I'm going to show in all directions. From which direction it is coming? He will say, okay, from the right side. From the down, from up, from his left side, like this, right? So this is his projection of rays. So here the PR stands for projection of rays. So when you say projection of rays, now this is depicted like this only, okay? So we generally will quickly depict, okay, this one he was able to say or this one he was not able to say in this direction. Accordingly, we are going to write it as plus or minus. So when you say projection of rays, we are actually indicating the health of peripheral retina. And this can get affected even with PL being positive and all. This mainly can get affected in diseases which will first involve the peripheral retina, right? So what are the diseases you can commonly think of at your level where you can say, okay, PR can be defective? Retinitis pigmentosa, even glaucoma, right? Even glaucoma, it starts from the periphery, right? So these are some of the important pathologies where this PR can be, you can get PR is affected. The perception of your projection of rays are affected in glaucoma and retinitis pigmentosa. Retinitis pigmentosa. Got it? Okay. So we all know what is light sense. So next is your form sense. What is a form sense? When you can actually look at things, right? So suppose this is a glass, this is a table, this is a laptop, this is a light. So all this is what? These are your form sense. So there was a question here in your exam that visual acuity is a measure of which sense? So of course we are talking about form sense, okay? Visual acuity is a measure of, is it a measure of light sense? Is it a measure of form sense? Is it a measure of contrast sense or color sense? It is form sense. Easy? Okay. So when we talk about visual acuity, we have to understand most commonly, of course, you're measuring it by Snellen's acuity chart. So what is the size of letter is determined by? So we have to understand, suppose this is the big E. Let's draw it or write it together. If this is the letter E of 6 by 60 we are talking about. It can be A, E, whatever. So we have to know that size of actually every letter in the Snellen's box. We are saying the scientific basis is that the size of every letter subtends an angle of 5 minutes. And margin of the letter means this and this, subtends an angle of 1 minute. Right? Where is this angle formed? At the nodal point of the patient's eye. So when you say nodal point of the patient's eye, do you all remember I've discussed this already? What is a nodal point in the introduction chapter itself? It is your optical center of the eye situated just behind the lens. So at the nodal point, every letter of this Snellen's box is subtending an angle of 5 minutes, margins 1 minute. It gets little difficult to understand this or believe this is such a large letter and downmost is such a small letter. Every letter is subtending an angle of 5 minutes and 1 minute. This is how a Snellen's box is made. How confusing. What is different then? Different is the distance. Have a look. So what we are saying that the largest letter is subtending this angle at 60 meters. And the smallest one is subtending this angle at 6 meters. Got it? So what we are saying that DNHO-BUC is subtending 5 minutes and 1 minute at 6 meters only, 6 by 6. But 6 by 18 means that OLAF, this is subtending that 5 minutes and 1 minute at 18 meter distance. This is at 60 meter distance. Have you all remember in our physics we have learned this, that the size of image not only depends on the size of object but also the distance of the object from the lens. Okay, so keep this in mind. This is one thing you have to know about Snellen's box and acuity chart. Second important thing is why 5 minutes and margin 1 minute, because it is made like this. If you look at this letter, every side has 5 limbs. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right. So this is the reason. Just remember this, very simple. And this is the Landolt ring which we are going to use. We generally use for what? For the illiterates, who are not able to read the letters. So this is how we are making one square. That square has small 5 squares. And this is one small square is 1 minute. And the whole 5 will be 5 minutes. And the whole letter therefore is always into 5. I think now it's absolutely clear to you all. You have to know all this. It's important. Okay, and what if the patient is not able to read even 6 by 60? If the patient is not reading 6 by 60, you ask him to move further 1 meter. So if he can read, his visual acuity can be 5 by 60 from 5 meters. Suppose even not, then it can be 4 by 60. Nahi, to 3 meters say 3 by 60. Then 1 meter say 1 by 60. And even at 1 meter, if he is not able to read, now you ask him to count the fingers. That is called your finger count. If he can't count the fingers from 1 meter, now what next? We go for hand movement, right? So either you show him the fingers, how many fingers if he can count, otherwise you move the hand and can you actually perceive a moving hand or not? And even if this is not there, of course, then we have to check the PN and PR as well. Okay, so this is how the sequence is. So if I ask you which is the minimum visual acuity on the Snellen's chart, what will you answer? Minimum on the Snellen's chart kya ho jayega? 1 by 60, isn't it? This is minimum on Snellen's chart. We are talking about on Snellen's chart. And what will be the maximum acuity on Snellen's chart? Maximum, think with me. Think with me, maximum acuity kitna hoga? Is it 6 by 6? No. Some people can be even 6 by 5 and very rarely 6 by 4 or 6 by 3, but that is rare. But yes, 6 by 5 is still little common. When we are talking in a standard term, 6 by 6 is considered the normal visual acuity. But yes, the best acuity on Snellen's, if I ask you, can be as good as, reported till now, as good as 6 by 4 or 6 by 3 as well. Okay? Just know this. Next we talk about what is hyperacuity, which we also call stereo acuity, or we can call it vernier acuity. So as you see this is your resolution power of your eye. What is the ability to differentiate two nearest points, right? So it detects the smallest difference between two nearest points. And this hyperacuity, so you can just say like this, that it measures our resolution performance of our eyes. Let's note down. So, measures the resolution performance. Okay, before you write this, let's understand more little here. Have a look. Which are the nearest points that I am able to catch hold of? That is my resolution point. Hai na? So, these 2 points, this is the space between, this will be called the angle of displacement. So, what is the normal value? Let's have an idea. It is 2 to 5 arc seconds for humans, right? So, it's not in minutes. This time we are talking about seconds. So, 2 to 5 arc seconds for humans. This is the resolution or hyperacuity of a normal human. Now, this you can get in people who have a normal 3D vision. That means you should have your depth perception. So, normal 3D vision is a requirement for this hyperacuity, right? And of course, the hyperacuity depends on spacing of the retinal receptors. Okay? So, these points are enough to know what is hyperacuity. 2 to 5 arc seconds. Okay, so next we talk about is the Snellen's chart the whole soul and the best? No. Why not the best and which is the best? The best one is this one. Let us note down one thing. If you look at the Snellen's acuity, can you see the first line has only 1 letter, the second has 2, then the 3. That means number of letters in each line are different. But in this chart, you will see that the number of letters are same from above to below. This is what is called logMAR chart. Okay. So, logMAR chart, log of minimum angle of resolution based on that. Okay. logMAR chart, or you can call it, it is also called as ETDRS chart. Just know the name. What is the advantage? The testing is not done at 6 meters. It is done mainly at 4 meters. The advantage here is it is considered first of all more accurate, and because the number of letters are same in each line, it negates any phenomenon of, negates the crowding phenomenon. Let's understand what I mean by saying negates the crowding phenomenon. So what happens is sometimes, especially this is a feature of amblyopia, what happens that same size letter, the size is, when it is presented independently to the child who has amblyopia, he can read that. But when it is presented with many letters, he is not able to read. That is called crowding phenomenon. So it negates this factor of crowding phenomenon. Therefore, it is considered more accurate. Okay. So this is also the same. That is the logMAR chart. And what do you call this chart is called? This is mainly for illiterates, where you're going to ask where the mouth of the sea is opening, right? So this is, the name is Landols broken ring test. Landols broken ring test. To be very honest, even if you experience that I have while checking in the OPD, it's such a big task to check a visual acuity of these people, because reason being, sometimes even if you're just asking which direction it is opening, the same letter they will tell you 2 directions, and then you are totally messed up. Right? We have faced this so many times. Anyway, you should know Landols broken ring test is done for illiterate. Is there anything else we can do? Yes, this is your tumbling E test. Okay, just know the names. This one is tumbling E test. So these are the tests which can be, these are the charts which can be used for illiterates to assess their visual acuity. Talking about the near vision, of course, the near vision, we can go for Geiger's chart. You should again be familiar with the name Geiger's chart. Right? What can be the other names? We also have Snellen's for near, Snellen's chart for near. Right? Then, few more names like Roman. And even the logMAR and ETDRS version is available. So, logMAR ETDRS chart for near. This is again available for near. So, you should just be familiar with the names regarding near, how to test the near vision. We also have the logMAR version and ETDRS version for these charts for near, right? So here just what is the method? We keep it at a near distance and we read the letters and we are again naming it like this, n by 6, n by 9, n by 12 and so on, right? So once you are very, very clear about the Snellen's equity chart and what is the meaning of 6 by 6, 6 by 9, what is the actual concept around it, now we are going to solve a few questions. This is very important and this is how they ask you in the exam. So let's see how to solve it. We will read this together. What is the angle subtended by the largest letter in the Snellen's chart on a person's eye who is reading it from a distance of 6 meters? So what do you know? The question is angle subtended by the largest letter. Which is the largest letter? It is 6 by 60. Okay. So what is the angle subtended at 60 meters for this letter? Do you understand the question first? The question here is, at 60 meters, we know that the largest letter subtends an angle of 5 minutes. The question here is, what is the angle that is subtended at 6 meters? What is the angle subtended at 6 meters? Okay? Largest letter means 6 by 60. So the tip here is, we first calculate the minimum angle of resolution. And minimum angle of resolution is nothing but the angle subtended by the margins of the letter. Subtended by the margins. Am I clear here? This is minimum angle of resolution has to be calculated. And I have already explained you have to just multiply it by 5. So, what is the minimum angle of resolution at 6 meters for any equity line is a very quick method. Just reverse the fraction. So, it becomes 60 by 6. Okay? Always reverse the fraction. You get a minimum angle of resolution at 6 meters. So, this is 60 by 6, which is equal to what? 10 minutes. So, this is MAR at 10 minutes. That means the whole letter will subtend how much angle at 6 meters? 10 into 5. So, this is equal to 50 minutes. This is the answer. Okay, and it's an important exam question. Let's try one more example to be clear. Suppose I ask you, the next question I'm placing here. Tell me what is the angle subtended by 6 by 12 line at 6 meters? Again, I'm repeating the same concept. When it was at 12 meters distance, this 6 by 12 line will subtend an angle of 5 minutes. But we are saying, what about not at 12, but at 6 meters? Again, it's very simple to find the minimum angle of resolution. At 6 meters, we just reverse the fraction. It becomes 12 by 6, which is equal to 2 minutes. So, the whole letter is going to subtend an angle of, you will answer 5 into 2, which is equal to 10 minutes. Is it now clear? Absolutely. Okay? Okay. So, that is one thing. So, we come to the next question. So, just to understand that everything has to be based, the calculations have to be based on minimum angle of resolution. Okay. So, when you talk about this patient with a visual acuity of 6 by 24 has to travel what distance to see the last line as 6 by 6? First, understand the question. Even in the previous question, many people don't understand the question. What was the question? Angle subtended by the largest letter from the distance of 6 meters. Now, I think after my discussion, you are clear with this one. Coming to this question, he is saying that the acuity of the patient is 6 by 24. That means, what will be the minimum 6 by 24? That means he is sitting at 6 meters. The question is how much he has to travel so that he can read the last line. So, when it is 6 by 24, I told you everything is based on minimum angle of resolution. What is the MAR? MAR is equal to 24. I told you reverse the fraction. So, it becomes 4 minutes, right? And now we are saying he has to read the last line 6 by 6. So, we know that here the MAR is going to be equal to 1 minute. Now, let's take it like this. The ratio, if there is a 4-minute MAR, right, then he is reading this at 6 meter distance. He is at 6 meters. So, if we want a minimum angle of resolution as 1 minute, how much distance? So, how much distance he should sit at to read 6 by 6? It is x. So, let's cross multiply it. 4x is equal to 6. So, x becomes 6 by 4, which is equal to 1.5 meter. At 1.5 meter, he should be sitting. But they haven't asked you this question. The question is, how much distance he will has to travel? Be alert. He was sitting when? Where? At what distance? 6 meters. So how much he has to travel is 6 minus 1.5 meters. Okay, so the distance to travel will be 6 minus 1.5. So this will becomes your answer. Let's talk of one more. A patient has a visual acuity of 6 by 36. At what distance will he be able to see 6 by 6 at Snellen's chart? A person who has a visual acuity of 6 by 36. The minimum angle of resolution here will be 36 by 6, which is equal to 6 minutes. Right? So when he is 6 minutes of visual MAR, minimum angle of resolution is happening by at 6 meters. So if we need an angle of resolution as 1 minute, what will be the distance? So what is the distance? It is cross multiply, it becomes 6x is equal to 6. So x is equal to 6 by 6. This is equal to 1 meter distance. This time they haven't asked you how much distance to travel. So this becomes our answer, that is 1 meter distance. Right? So this is the reason why you need to have a very important concept regarding the Snellen's acuity chart and the angle that is subtended by the whole letter, and by what is minimum angle of resolution, which is the angle subtended by margins of the letter. Right? Okay. Next, we talk about how to assess the visual acuity in the different age groups. We'll be talking about in infants. What about in preschool children, as school-going children and adults? So, just simplified like this. Okay. So, first is infants. So, children who are either newborn or till 1 year of age, how do you assess the visual acuity? What are the things we can do? Number one is preferential acuity tests. Right? So, first is your preferential acuity test. Means, this is based on preferential looking. You are attracting the child to look at something and then you are trying to grade it. Okay, is he able to observe it or not? Let's see what I mean. So, preferential acuity tests can be main important ones that you should be familiar with are Teller's chart and Keeler's chart. What is the Teller's chart? It is like this. So, what is the Teller's chart? If you see here, this child is shown the gratings, and the spatial frequency of the gratings will be the measure of the visual acuity. How close? If the child can detect very close lines and gratings, that means the acuity is better, right? Isn't it? So, just understand this way. So, we can just note it down like this, that what spatial frequency the child can detect, right? This is what you are seeing, what spatial frequency the child can detect. Okay? Okay. Similarly, is this one. These are the Keeler cards, again based on the same preferential looking. Okay, and again the spatial frequency is what we are trying to assess in these children. Okay, Keeler's card. So this is the next one. This is also preferential acuity testing, where it's based on the same thing, that we are going to assess the spatial frequency in the child, how much spatial frequency the child is going to detect. What was the next method? Next was a very newborn or even a very small child. What we can do, you want to know whether the visual pathway is fine or not. Then we can go for OK drum test, which is optokinetic drum test. So this has been asked in an exam with like this, written as OK drum test. So don't get panic. So many students, when this exam happened and came to me, so students were, ma'am, ye kya tha? What was OK drum test? So OK was nothing but optokinetic drum test. Okay? Mera OK alag hai. Anyway, so this optokinetic, so do you remember when neuro-ophtha, what is optokinetic? With the saccadic pursuit and saccadic pursuit, saccadic movements. So whenever your eye is seeing something rotating or moving in a rhythmic manner, cyclic manner like this, there is some movement in your eyes, that is pursuit and saccadic movements, isn't it? Okay. If you know this, I had given you example of one train is passing and you are also sitting on a train and another train is crossing you. You're seeing at every passenger one, then the next one, then the next one. So now I think you remember. This is what is optokinetic nystagmus. What do you do with the OK drum test? That you are showing this child this rotating drum, and if the visual pathway is fine, I can see those movements in his eyes. So presence of optokinetic nystagmus is there. This means that at least this child has a vision of equal to, or so at least he has a vision of equal to 3/60. So have a look. This is what is optokinetic drum. There's another term. What is Cadford drum? Cadford drum is also based on the same principle. Instead of the lines, there are dots. Okay? Dots, not lines. This is called Cadford drum. The third method to see any activity, whether the visual pathway is fine or not, is electrodiagnostic test, that is VER, visual evoked response. We also call it visual evoked potential. Okay? So what is visual evoked potential? It tells the activity from ganglion cell layers till the visual cortex. It is the activity from ganglion cell layer till the visual cortex. Hope you all remember your visual pathway. And the normal time that it takes is, what is the normal VER response? Duration, normal duration is, please remember this, was once asked in your exam, it is 124 milliseconds. Okay? It is 124 milliseconds. One more thing, we were talking about hyperacuity, if you remember, and the normal value is 2 to 5 arc seconds. Do you all know what is the resolution power of your eye? In megapixels, do you know how many megapixels? Resolution of your eye is 576 megapixels. Okay. Okay, coming back to assessment of visual acuity now in preschools. Preschoolers, first we will learn, most important is Cardiff Acuity Test. So what is a Cardiff? It is not but just a cardboard. All these designs being engraved on a cardboard like this. Okay. So if the child is very small, of course, then it is more of an objective test where I will see whether the child is attracted with the figure that is formed or not. So it becomes a preferential looking test only for Cardiff. But if the child is older in a preschool age, he will tell this is a fish, this is a house, this is a tree. So he will be able to tell that. So it becomes more of a subjective test. So just remember, Cardiff can be, depending on the age, in less than equal to 1 year. It is more like an objective test. It's a preferential looking test. But objective and a subjective, I hope you understand. Objective means that the observer is going to see, patient is the subject is not participating. But when the subject is participating, that is called subjective. So more than 1 year till preschool, that is around 4 to 5 years. Now this becomes a subjective test. Simple, common sense. What is the second one? Just know the names. First is this. Second is Sheridan-Gardiner test. These are nothing but different sizes of HOTV. So the letters that are written in asked to read are limited. That is only HOTV. Okay, of different sizes. This is your Sheridan-Gardiner test. Again for preschools. Third is your Allen picture test, where we are shown different types of pictures and the patient has to tell what he is seeing. And have a look. So this is what is Allen test cards, where the patient is going to recognize the picture and tell, right? And what is the fourth is? The fourth is your STICA test. What is STICA test? This is mainly for mentally retarded children. So STICA stands for Screening Test for Young Children and Retarded. What you do, you give a picture in his hand and he has to match that picture that among the pictures that are presented to him. Something like this, okay? So it is more of a matching. Suppose this is given, then he has to match it with the house and so on. But what I mean to say is the child is given a test type and he has to match that picture to the pictures that is presented in front of him. This is your STICA test, right? And of course, when you talk about school children and adults, we have already done that in so much of detail about Snellen's chart. We have talked about Logmar chart. And of course, when we have say for illiterate, Landols, broken ring test, tumbling test, and for the near we have talked about is Geiger's chart. Just a quick revision. So these are the different methods of assessing the visual acuity. So if you talk about, when we were saying about the newborns and the children or infants or children of less than 1 year, we can do optokinetic nystagmus test, OK drum test, or we can go for VAP measurement, right? Yeah. And of course, if infant age, we can go for also for preferential looking tests, isn't it? So to all of you, what is the visual acuity of a newborn? This is the next important point. Visual acuity of a newborn is anything around 6/60. And what is the refractive error in a newborn or an infant? This is also another important question. You should answer hypermetropia. Don't answer hypermetropia with astigmatism. That's also given in options and you all get confused. No, it's only hypermetropia. Okay? So, what are the points to know? That initial vision is less than equal to 6/60. Okay? Now, this low vision, why a newborn has a low vision? There are two main reasons. One, I just said, is hypermetropia. And secondly, do you remember we talked about foveal reflex formation, which starts at 6 weeks? And it is only going to mature when the light rays are falling on the fovea. The fovea gets the sensory stimulation, and therefore the foveal reflex formation starts at 6 weeks and it finishes by 5 to 6 months. You remember we have talked about this? Right, so when the fovea is immature in a newborn, 6 weeks it will start. So that is also a reason why the vision is 6/60 or less than 6/60 is more accurate to learn. Okay, so this is the reason why the child has such a low vision, because the fovea is not mature, and secondly, the child is highly hypermetropic with a very small eye. Maximum growth of the eye takes place by 2 years of age. Till 2 years, the eye maximum growth will happen. After 2 years, it may change a little bit, and those mild changes, sometimes it progresses to myopia or hypermetropia, like this, you have to understand. Okay, but maximum growth of the eye takes place by 2 years. Initially, an infant is always, you will learn hypermetropic. Take it? Okay. There was one more question I'm reminded of. When will this child, at what age the vision goes to become 6/6? Visual acuity becomes 6/6. So we are saying the newborn visual acuity is 6/66, 6/60 or less than 6/60. When will the visual acuity become 6/6? Which age? Generally by 6 years. Please learn. Easy to learn. Everything is 6 here. So generally by 6 years. Okay, so this was your exam question. Okay, next we talk about, what is this? What are you looking at? Yes, we all know we are looking at pinhole. Okay, so once we were talking about the foveal reflex, another method of assessing the visual acuity in a child can be Menis reflex. Just know what is Menis reflex. So we can incite the Menis reflex only when the fovea has developed. That is around 5 months of the age. So what is a Menis reflex? You show torchlight in front of the eye and a bright light in front of the eye, and you see the child start blinking, right? So this is what is called Menis reflex. Torchlight, bright torchlight, or bright light, you can just say, right? This causes blinking. But this is again only possible if the fovea is developed, right? So this will be around after 5 months. We can see this after 5 months. So just know what is Menis reflex. Okay, so we next talk about, yes, so we are talking about, this is a pinhole. Can you see this opening? This is your pinhole. So when you talk about pinhole or pinhole test, what do you actually understand? What is the pinhole doing when you are putting it in front of the eye? It is cutting all the peripheral rays, isn't it? So what the pinhole is doing is, it is cutting the peripheral rays and only the central rays are passing through the hole. Hence, it increases your depth of focus, right? Once you know this, the role of the pinhole, what are the questions asked and what is the pinhole test? You have given some number to the patient. Now, when you put the pinhole, if he feels more improvement in his vision, that means some remaining refractive error is still there. And if there is a deterioration of the vision, common sense, you are looking through a pinhole, there is deterioration of the vision, means there is some central opacity, whether it is corneal or lenticular opacity, or secondly, what can be the possibility? There is some macular lesion, right? So we all should be very clear about what is a pinhole test. When putting the pinhole, vision is improving, it is the refractive error. And if there is no improvement, rather there is deterioration, vision is decreasing, okay, then either there is central opacity, which could either be in the lens, lenticular, or it could be a corneal opacity, or secondly, it could be just a macular disease. This is what is a pinhole test. Next question they ask you is, what is the size of the pinhole? What is the size of the pinhole? We will say 1 millimeter or 1.2 millimeter. Both are correct. And then another very interesting question was once asked in your INICET exam, I suppose, that how much can be neutralized by the pinhole? What amount of diopters? Do you understand the meaning of this question? Suppose the patient has some refractive error. Without using specs, only looking through the pinhole, he is able to read 6 by 6. This is what we mean, that the pinhole is neutralizing those diopters. So actually what I have seen practically observed is around 2, but theoretically it is said that we should answer till 3. So let's answer that this can neutralize up to 3 diopters. This is I'm telling you in relation to one question, up to 3 diopters. So these are the questions around pinhole. Okay, next, what do you look at? We are looking at stenopic slit. So this is a opening which is in form of a slit. This is what we call stenopic slit. So the first thing is measurements. What is the width? 1 millimeter. And length of the slit is 15 millimeters. Let's learn together. 15 millimeters. So where do we use the stenopic slit? Do you remember the Fincham's test that we have studied together? So that can be one use of stenopic slit. And that is Fincham's test, right? So one is Fincham's test. You all remember Fincham's test? The patient is seeing the colored halos. You pass the slit in front of his eyes, and if the halos break, this is due to immature cataract, and if it does not break, this is your acute congestive glaucoma. This we have already studied. Okay, what can be the second application of stenopic slit? Is to detect the axis in astigmatism. And number 3 will be site of iridectomy. So suppose you have to do an optical, what do you call it? Optical iridectomy has to be done to create a second pupil, right? If there is any central opacity, we can do an optical iridectomy. You can just use the stenopic slit to assess where the vision can be best and maximum, and then you do the iridectomy accordingly, right? So to assess the site of optical iridectomy. These are the 3 main roles of stenopic slit, right? So once we are clear with this, we come to the next sense, was contrast sense. When you say contrast sense, how do you actually define contrast sense? It is any ability to distinguish the object against its background. So ability to distinguish any object against its background. This is what is contrast sensitivity. So contrast sense, right? So contrast sense is generally decreased in which conditions? You just keep in mind it can be less in amblyopia, where you see a decreased contrast sensitivity, or second is in some optic neuropathies. So once you know what it is and which are the conditions where it can be affected, we talk about what are the tests of contrast sensitivity. Most commonly that is used and you should know about, which has been asked, is your Pelley-Robson chart. Then we have Arden. What is Arden gratings? What is the FACT test? This is functional acuity contrast test and Sparks test. So one by one. Pelley-Robson is just a letter chart like this, and if your contrast sensitivity is good, you will be able to read it nicely. So this is your Pelley-Robson contrast sensitivity chart. Is it okay? What is the next thing that we have to keep in mind is Arden gratings. So you have the gratings in the different contrasts, and if you are able to actually see and appreciate these gratings, then your contrast sense is good. So second is your Arden gratings. When you say functional acuity contrast sense, here you can see the lines are in the squares different directions. So we have to just tell whether it is right or it is up straight or it is directed on the left side this way. So the lighter and the lighter lines, are we able to catch hold of it or not? Okay, next, lastly, this is Sparks test. Sparks test is Spieth-Richman contrast sensitivity test. It is specifically useful for people who are a little mentally retarded. The person has to just see and tell where he can see the gratings, right? Like in this case, okay, in which square we can find the gratings. So we were just talking about that this contrast sensitivity can be affected in optic neuropathies and in amblyopia. So let us also understand that we sometimes measure this contrast sensitivity in glaucoma patients before the visual field effect is manifested. So there has to be some level of damage before any field effects will come. So before that, if you want to know that there is some effect and there is some damage going on, we can just see the contrast sensitivity. Okay, so if you look at the contrast sense of that patient and we want to assess the patient, glaucoma patient, before appearance of visual field defects. Just let's know this because visual field defects and scotomas only appear after one level of damage has happened. Okay, next is your color sense. So when you talk about color sense, first important thing to know is it starts at 3 months. Why do you learn this? Because again, we need to have a good foveal reflex. And what is the foveal reflex formation starting at what time? From 6 weeks to 6 months. So generally, we should have some maturity of fovea in order to appreciate the color, right? So this is the reason, because the foveal reflex will form foveal reflex formation, or you call it macula maturation, is going to take place in this time period. And at that time, around 3 months, the color perception or sense is starting. First important point, right? Okay. Then when you talk about the color sense, okay, so let's have a quick revision regarding our VIBGYOR, how a white light can break into these 7 colors, right? And before this V-violet, we have the ultraviolet range, and after red, we have the infrared range. Okay? And we should also keep in mind that more the wavelength, less the deviation. So the red side deviates the least, and maximum deviation will occur in violet when the white light is passing through this prism, and this is how it is breaking into these lights. Okay. So once we know this, we will be talking about ultraviolet rays can be A, B, C. Okay. So what about things related to our eye that you have to keep in mind? That ultraviolet A are the rays which are absorbed by the lens. Okay. And ultraviolet B and C are absorbed by the cornea. So, it is absorbed by the lens. Therefore, on the blue side, blue color is generally less appreciated. Or you can understand this way, that when you operate a patient for the cataract and you have removed the lens, he starts seeing a lot of blue, because that was not earlier being appreciated. Okay. Sometimes we even have to put a IOL, which is more blue light absorbing IOL, if that is so disturbing to the patient. So this is an interesting piece of information, and I hope you will remember this, that when you are operating a cataract, the patient starts seeing more blue. Some patients are really hassled by it. Okay. So this is one piece of information you keep in mind. And what next that is relevant to you is about ultraviolet B. So do you all remember what ultraviolet B is causing in your eye? Let us revise. One, it causes pterygium, right? And what is the other thing that it can lead to? Is snow blindness. So pterygium and snow blindness. What is snow blindness also known as? We call it photophthalmia, or we call it photokeratitis. So what is photokeratitis or photophthalmia? I think we have taken this in the earlier chapter. So what is that? Why do you call it snow blindness? Because ultraviolet B rays are reflected from the snow and injure your cornea. It is leading to corneal erosions. How do you treat it? We just patch it with antibiotic ointment. Patch and bandage it with antibiotic ointment, right? So keep that in mind. So this is one thing, snow blindness or photokeratitis, which is being caused by UVB rays, and one is pterygium. Okay, quick revision here. And when you talk about what is then photoretinitis, we all remember it is through infrared rays. What did you learn? When you're directly looking at the solar eclipse with unaided eye, this is the time when this patient can develop an infrared injury leading to photoretinitis, which is characterized by macular burn. And this will finally lead to macular scar. Right, so that was a quick thing here. We next coming to what is the basic theory of color vision. So there are 2 theories, trichromatic theory and opponent theory. We generally follow the trichromatic theory, and it was given by a scientist Young-Helmholtz. So we also call it Young-Helmholtz theory, or Helmholtz theory of trichromatic theory of color vision. Now what is this theory saying? That there are 3 types of cones, right? Large cones are responsible for the red color, medium cones for the green color, and small cones are responsible for blue color. So there are 3 different types of cones for the 3 primary colors, red, blue and green. And it is a combination of these 3 through which we are able to appreciate so many colors. Okay, so short wavelength is blue, medium is green and long is red. So when you talk about color blindness, There are two ways you can actually classify or learn the types of color blindness. One, according to this theory, we can divide it as trichromatic, dichromatics, or monochromats. When you say trichromatic means all three types of cones are there, but one of them is weaker. So there's an anomaly. So if red is weak, we call it protanomaly, deuteranomaly for green weakness, and tritonomaly for blue weakness. These are all trichromats. When you talk about dichromats, now only two types of cones are there. That means one is absent. So now we call it opia. Okay, so protanopia is the red blindness, deuteranopia is green blindness, and tritanopia is blue blindness. So which is the most common type of color blindness? Exam question, you answer, it is deuteranopia. Okay, monochromats. Only one type of cone is present. Therefore, the patient is not able to see any colors except different shades of grey are perceived. These are monochromats. Okay. Another way of classifying is congenital and acquired. So when you say congenital color blindness, what are the points we will remember? This patient is generally, what is the inheritance? X-linked recessive. That's why it is the males which are involved most. Color blindness is most common in males only, primarily affecting the males, and this is X-linked recessive. Then, of course, it does not affect the vision. It's only the color vision faculty which is affected. Visual acuity is normal and it is not going to be progressive as well. Okay, so let's learn these points. Important. First, it is non-progressive. It will not worsen with time, and vision is normal. And what type of blindness is primarily? It is a red-green blindness. So that was about congenital color blindness. Coming to acquired, when you say there is some disease because of which this has happened, so it is therefore progressive and visual acuity will be reduced. So when you say acquired, it can either be retinal disease or optic nerve disorders. So when you say optic nerve disorders or retinal disorders can lead to color blindness, are you learning with me? They are the cause of acquired color blindness. So there is no need to mug up. Common sense, if optic nerve disease is there or retinal disease is there, naturally there has to be, if these diseases are there, there has to be diminution of vision. Okay. Now before I move, one very interesting thing. So suppose you have a patient to whom you are showing a red color and asking, he is a patient of color blindness. Okay? He is color blind. Now you show him a red color. So what will he say? What is this color? If he is a case of congenital color blindness, he will call it red, because that red term is a learned behavior. He has been taught that this is red, so he assesses that this type of picture is red color. So a congenital will actually answer you correctly that okay, this is red, right? But when you talk about acquired, he actually knows which one was red, so then he will not say this is red, right? For him, this is not red, right? Okay. So hope you have understood this. This is just an interesting piece of information that you should know. So if you're showing a red color to a patient who is a color blind, and if he's a congenital color blind, what will be his answer? Don't say grey. He will still call it red, though he's actually not seeing that red. Okay? So it's all learned behavior, right? Now when we say, coming back to acquired color blindness, it can be due to retinal disease or optic nerve disease. Let us understand that if it is through optic nerve disorders, it is generally a red-green color blindness. And when you talk about the retinal diseases, right, then this is generally your blue and yellow disorder. Okay, blue and yellow. So when you say retinal diseases, here we mean, this is called Kollner's rule. Okay, interesting. This is your Kollner's rule. So Kollner's rule says that optic nerve, so the green leaves means red and green generally is gone in optic nerve defects. And when you talk about the outer retina, right, optic nerve and of course the inner retina, we can add it here where we have written outer retina means inner 6 layer, outer 4 layers. So outer retina, it is mainly the blue, yellow. Okay? So optic nerve and inner retina, you can include that here. Inner retinal layers, it is mainly red, green, and outer retinal layers, outer 4 mainly, it is yellow. Okay? Okay. There are 2 exceptions to this rule. Let's know the exceptions. What are the exceptions to this rule? One you will learn is glaucoma. Okay? So glaucoma Though it is an, of course, optic nerve problem, but we don't have red-green blindness there. And second exception is Stargardt's disease, okay, where you don't get a blue-yellow defect. So let's remember this. We next talk about what are the tests of color blindness. When you talk about the tests of color blindness, one is Ishihara chart. Let's have a look. So tests for color blindness, first is Ishihara chart, isn't it? So this is what is Ishihara chart, and it is mainly used for screening purpose. So in every eye OPD, you will see this is like a book with different plates, okay? It can have around 24 plates book, or it could be a 38 plates book, whatever it is. So these plates are there and the patient is asked to read the numbers on the plates. The minimum visual acuity that should be there for this to be read is 6/18. The patient should have more than 6/18 vision in order to be this being a reliable mode of screening, right? And it will only catch, another very important point, red-green blindness. It catches red-green blindness. An interesting part is the first plate is always written as 12, where both individuals, normal as well as colorblind, can read. Okay, that first plate. What we have to know is that if this patient is not able to read less than 9 plates, he is definitely colorblind. Okay, so less than 9 plates, then he is definitely colorblind. Right. We next talk about in children, what we can do is we use this Hardy-Rand-Rittler test. Okay, where the children can actually see the shapes. So this mainly contains the shapes. And here it is not limited only to red-green blindness. That's another important point. So this is used in children. What is the third test? The third test is Farnsworth-Munsell 100 hue test. So Farnsworth-Munsell, actually there are only 85 caps, though it says 100 hues. And you have to arrange it in the color progression. Okay, arrange it in color progression. You have to arrange in darkness or arrange in color progression. Okay, so mainly this is used for quantification of color blindness. Okay, so this is used for quantification of color blindness. Next, we can use, this is a Nagel's anemaloscope. This is also an instrument which is used for quantification of color blindness. Just know the names, right? And what is this? This is Eldridge Green Lantern test. Mainly it helps in classification of color blindness. Even this is, nobody is going to ask you, but just know, be familiar with the names, that's enough. There's one more university color test. What is this? You just take the central dot and you match it with the rest of the dots. The central color is matched with the peripheral options. This is your city university test. So actually there are many more. We are just taking up the most important, which is important for us. This one is even a little extra point, but otherwise there's no end to the number of color tests that we have, right? So this is your city university test. What did we say? We are matching the central color with the peripheral color to assess the sense of color, how much we have in our eyes. You got it? Okay. Next is your Purkinje images. The next is Purkinje images. Do you all know what are Purkinje images? So what are Purkinje images? Purkinje images are mainly the images which are formed on your major refracting surface of your eye. What are the major refracting surface of your eye? Cornea and lens. So image that is formed on the cornea, this is image 1 on the anterior surface of the cornea, right? Image formed on posterior surface of cornea is 2. Then anterior surface of lens is 3. And posterior surface of lens is image 4. This is how it has been made. Okay, so what are the questions that are asked here? First question, which are the images which are absent in aphakia? So you all know it is 3 and 4. Okay, so images absent in aphakia, common sense, we will answer it is 3 and 4. The next question is, which image is inverted? So we all know this. You remember we have learned together how the parallel light rays are falling on the cornea, on the lens. They bend at the nodal point, and at the nodal point the light rays cross, image gets inverted, and it is the same inverted image which falls on the retina. So which is inverted? It is image 4. So this is inverted. Image 4 is inverted, right? Then how many images are there in pseudophakia? If you're using an artificial lens, we will answer all 4 images. All 4 images are there in pseudophakia. Okay? Next question that they ask you is, what about mature cataract? So let us learn that in mature cataract, it is the 4th image which is absent. So there are only 3 images in mature cataract. Okay, so so many questions out here. Only 3 images. 4th is absent. 4th is absent. Right? Hope this is absolutely clear. So have a look. So this is it. This is the cornea. This is the lens. So here we are just showing you, if this is the light which is falling, the first, second is on the cornea, 3rd and 4th on the lens. So one more question for you. Which image are you using when you are doing keratometry? So in keratometry, we are dealing with anterior surface of the cornea. Since we are dealing with anterior surface of cornea, what is the answer? It is image 1. Okay, so for that, it is image 1. 1 in Roman number we will write. And if you have to see the depth of anterior chamber, it is 2 and 3. Depth of anterior chamber, it will be 2 and 3. I think now the basic is absolutely clear to you all. Okay? Okay. Next we talk about ophthalmoscopes. So what are the types of ophthalmoscopes that you know? We all know what is an ophthalmoscope. Instrument to examine the retina. That is an ophthalmoscope. We also call it fundoscope. Okay, so we next talk about this direct and indirect ophthalmoscope. We also know that ophthalmoscopes are also called fundoscopes, isn't it? Right. So what are the points you have to remember? First of all, do you know how does a direct ophthalmoscope look like and indirect? I hope you are familiar with this. So here it is. This is your direct ophthalmoscope. We take very close to the eye. And what we are trying to see? We are trying to see the central retina. Okay. Why I'm saying central retina? Because at one time, the amount of field that is visible through this instrument is 2 disc diameter. What is 1 disc diameter? 1.5 millimeter. Right? Okay. And what is the image formed? It is virtual and erect. Right? And what is the magnification when you're using this instrument? We say it is, magnification is around 15 times. Okay? Into 15. These are some very, very important questions that I have just discussed with you. So what is the magnification, type of image, what is the field at one time, and therefore what you are going to use it for. Right? This is your direct ophthalmoscope. What is distant direct ophthalmoscopy? When the same ophthalmoscope, normally we have to take it to a very close distance and then only we can see the retina. If I am using the same instrument at a distance, now you call it distant direct ophthalmoscope. And distant direct ophthalmoscopy is done at, that is one point you have to know, it is 25 centimeters. This is also your exam question. 25 centimeters. What am I trying to see with the distant direct ophthalmoscopy? Aap kya bologe? Media of the eye. What is media? All the structures in the way of light ray till it reaches the retina. So, what we are saying? Media of eye means cornea, aqueous humor, lens, vitreous humor. All this is media. So, any opacity is nicely visible through distant direct ophthalmoscopy. Okay. Another important point that we have to remember regarding direct ophthalmoscope is how do you calculate the magnification of a direct ophthalmoscope? So, direct ophthalmoscope, the magnification is calculated as power upon 4. So, normally for an emmetropic eye, if the power is 60, so 60 upon 4, that's what is 15 times. Another question recently asked was, when you are looking at the right eye of the patient, which eye will you use yours? Which eye of the examiner is used? So, understand, if you are the patient, I have to see your right eye, I am going to use my right eye to see. For the left eye, I am going to use my left eye, okay? So, the same eye for the patient and examiner. Then they will ask you another question here. And that is, what are you going to instruct the patient? Should he look into the light of the ophthalmoscope or should he look straight? If he looks into the light, the pupils are going to constrict. So he will look straight. So this was about points regarding direct ophthalmoscope. Now let's talk about indirect ophthalmoscope. So indirect ophthalmoscope is mainly used to see the peripheral retina. Why? Because the magnification is only 3 times or 5 times. Okay, so magnification is either 3 times or 5 times. So this is used to see only the peripheral retina. Magnification is less, field is more, or magnification is more, then the field is less. So here, how much area we can see? At one time, it is 8 disc diameter. At one time, the area that you see is 8 into 1.5. Right? Type of image formed here is real and inverted. Okay? So this is your exam question, this is your exam question, and this is your exam question. Peripheral retina. Now when you see, as you can see here, the examiner, this is the light source, this is the lens he's using. So the next question is, what is the power of the lens? The power of lens can vary from plus 13 to plus 30. But most of the time, most commonly what is used is plus 20 diopters. This is another question of your exam. So if you see how that indirect ophthalmoscopy works, this is your examiner. The light source is shown, these are the mirrors. And the image is mainly formed between the lens and the examiner. That means image is formed somewhere here in the air. Okay. So this is another exam question. Where is the image formed? Between this examiner and the handheld condenser lens. It is formed in the air. Aerial image of the retina is formed. Okay. So let's remember this also. It's an important point. How do we calculate the magnification of indirect ophthalmoscopy? So magnification of indirect, this time the formula is power of eye upon power of lens. So if the power of lens, generally what I said most commonly what you use is plus 20 diopters. So power of eye, if I take 60 upon 20, this is around 3 times, right? Now suppose I say that the patient is hypermetropic by 5 diopters. What do you understand by that? Hypermetropia is less power. So if I say 5 diopters hypermetropic, what will be the total power in his eye? Please remember, in hypermetropia, total power is less. So it becomes 60 minus 5, right? So it is 55 upon 20. And if I would have said, okay, instead of hypermetropia, if I say this patient is myopia of 3 minus 3. Now what is the magnification? So total power of eye will become what? If he is myopic, myopia is more than required. So here the total power becomes 63. So it becomes 63 upon 20. So just keep this in mind. This concept should be very, very clear. If I am talking about myopia, I have to add the power to the emmetropic power because myopia is more than required. It is more power. Though we indicated with minus, it is more power, isn't it? And hypermetropia is less power. So that was about indirect. And how do we calculate? If they ask you, this is a little extra point, how do you calculate the magnification during slit lamp? So again, for the slit lamp, the magnification is same, power of eye upon the power of lens that you're using. Okay. And apart from that, we have to also add the slit lamp. We have to multiply with the slit lamp magnification. Okay. This is the total magnification through slit lamp. Right. So power of eye upon power of lens into slit lamp magnification. Even if you don't want to learn, it's okay. They haven't asked you this. Next we talk about is visual angles. What do you understand by visual angles? So let's learn like this. If this is the eyeball, an imaginary line which is dividing the eyeball into 2 halves. This is what? This is your optic axis. A line passing through the fovea. This is what? This is your visual axis. At the nodal point, this angle that is formed is alpha. Okay. So what is alpha? Let's have a look. We are saying it is the angle between. So this is the visual axis through the fovea and this is your optic axis. The angle between this blue and the green line, this is what is angle alpha, right? And this is generally at the nodal point. Now what happens is generally this optic axis is defined as an axis which is passing through center of the cornea. which is very difficult to assess what is the exact center of the cornea. So for our convenience, if we take center of pupil, and now I say that a line passing through center of pupil as pupillary line, then at the surface of the cornea, this is the pupillary line and this is again the visual axis. Now this angle is what is called kappa. So angle between the visual axis, this time pupillary line at the corneal surface. This is what is angle kappa. Okay. So there's hardly much difference. So alpha, what is the actual value is, of course, for convenience, I've made it so broad and all this just to explain you. Otherwise, it's only 5 degrees. Okay, there's not much difference between optic and visual axis. It's only 5 degrees. And almost same, the alpha and kappa are almost same except these very minor differences. So if you look here, this is almost, this red line is the pupillary line. Isn't it? So pupillary axis is almost merging with the optical axis. Isn't it? So almost the same. So between the pupillary axis and this green line visual axis, you know, this is what is at the cornea. This is angle kappa. Okay, so once we know what is angle alpha and kappa, let's understand something here. Suppose I'm examining your eye and I show the torchlight on your eye. So the torchlight, the light falls, if the eyes are absolutely straight, then the light is going to fall at the center of the pupil. No, actually it is never falling exactly at center of pupil, but little nasally, and that is considered normal. That means this is because we all have a very small positive angle kappa. What is positive? When the light reflex is falling nasally, we call it positive. When it is falling temporally, we call it negative. Just understand, I'm just trying to simplify things here. Okay, suppose you are showing the light on my eye, that in this way you will understand better. When the light are falling almost centrally, only slight nasally, it is slight small positive angle kappa. Now if that same light falls more nasally, do you realize when the light is falling too much nasally, which it can happen only when the eye is out. So it looks as if the eye is out, though it is not. It is only large positive angle kappa. So what I am saying is, positive angle kappa means that the light reflex falls nasally, and this is normally a small positive is normal, but when it goes too much nasally, I am saying it will look like that the patient is eyes are out, and that is not actually out, but due to this large positive angle kappa, that means it is a case of out is exotropia, and since it is not actually out, we call it pseudo-exotropia. Too much nasally means there is a large positive angle kappa. And this is mainly seen in patients of hypermetropia. So the point that we have to know here is a large positive angle kappa can be seen mainly in high hypermetropes and can be a cause of pseudo-exotropia. Can be a cause of pseudo-exotropia. Now we come to the next one is negative kappa. Negative kappa ka matlab, it means that the light reflects that in the torchlight when you showed on my eye, it's fall temporally, and it falls too temporally, it will look like as if the eye is in. So too much temporary, if the reflex is temporally, this is your negative kappa. And large negative kappa means too much temporally, and therefore that will look like that this patient has pseudo-esotropia, and this is mainly seen in which patients? Myopes. High myopes can present as pseudo-esotropia. So this is what you have to know. Okay? Samajh aaya? You are showing the light to my eye. If the light, I am quickly revising, light is falling too much nasally, it's a large positive kappa. It is a cause of pseudo-exotropia. This is found in high hypermetropes. If you are showing the light to my eye and it is falling temporally, more temporally means large negative angle kappa. It means temporal. If anything falling temporal means eye is in. That means pseudo-esotropia, and this is mainly seen in high myopes. This is what you have to learn, and this is why you are learning about angle kappa. And so once this question has been asked, all this information is not futile or I'm not giving you an extra information. Just know this. You should be knowing it. Right? Okay. So when you say large positive angle kappa, when I said large positive angle kappa, again for your quick revision, is what? A cause of pseudo exotropia, isn't it? Because it falls more nasally. So anything falling more nasally means the eye is out. I'm writing it again here for you all, and this is a cause of pseudo-esotropia. This is all you have to know about this is for hypermetropes, this is myopes. So this is what you have to know about your visual angles. We come to the next important thing is what are the different refractive errors that we are going to cover. So different myopia, hypermetropia, astigmatism, anisometropia, and lastly aniconia. We will not forget that. And even there are higher order aberrations which are called aberopia. You can consider it as a sixth error of refraction, but that goes a little extra point. Hence, I haven't mentioned it here. We'll mainly learn these 5. So first is your myopia, which is called nearsightedness. Now, we don't learn it like near because there's a lot of confusion then. So let's understand what is myopia. What do you have to know? Myopia, M for M means more power, right? So the refractive power in the eye is, the refractive power is more than required. It is more than required. So when the refractive power is more than required, what will happen? Too much of power, the bending is too much and it is going to bend even before reaching the retina, as you can see here, isn't it? So the light rays, if you want to draw it for yourself, the light rays are focused in front of the retina. So I need the focusing here, isn't it? So what I do? I have to decrease the power. How do you decrease the power? By using concave lenses. How much I have to decrease the power to focus on the retina? This will be the measure of my myopia. So kitna kam karna pada? What is the amount? How much I had to decrease the power is a measure. That is why myopia is always denoted as minus. So this is the concave lens, and what is this concave lens doing? Decreasing the powers. By diverging some of the rays, it is decreasing the power so that there is focusing on the retina. Okay? M for M, more than required, more power is myopia. Correct? Okay. So once we know this and we are clear about this, what else? Classification. How do you classify myopia? Very simple. When more axial length will be there, more axial length, it is again cause of myopia, isn't it? More axial length, number 1. So axial myopia, if it is due to more curvature, more is the refractive power. We have learnt it so many times. So more curvature can lead to curvature myopia. Then index myopia is due to more refractive index. This is your index myopia, right? When the refractive index is more, mainly for the lens, it is more, then it is your index myopia. And positional myopia. Positional myopia means when the lens is dislocated more anteriorly, then anterior dislocation is going to lead to positional myopia. So these are the 4 types of classification, how you can classify myopia. Now on exam, how will a patient of myopia present? Of course, there is difficulty in far vision. So either blurred far vision or diminished vision, the far vision is less, right? This is how the patient is going to complain or present, right? And on examination, what do you see? What do we see on examination? Instead of learning like this, let's make a diagram and learn this. So let's make a diagram. For on examination, a myope is going to have, I have taught you how to learn the ocular features. Always first make the diagram. This is the iris, this is your ciliary body, this is your lens, these are suspensory ligaments, this is your choroid, and the dotted one is your retina. A quick diagram here. Okay? Now one by one, how do you have to see? You have to just learn outside to in. So first outside, eyeball mein. Yes, it is long eyeball. Right? Long axial length, more axial length. Generally is seen. This is the first finding. Second, there can be more curvature also depending on this, more curvature. And because the eyeball is long, what you get is a deep anterior chamber. Right? What else? What about the ciliary muscles? They are hardly being used. There is already more power. I don't want to exert accommodation. So the ciliary muscles, they become weak. Ciliary muscles, they become weak, and sometimes later on they can even lead to atrophy. Okay, so this is another point. Okay, too much of elongation and axial length can lead to thin sclera. One more point, thin sclera. And what about the retina? Too much stretching can lead to a lot of changes in the retina, which we learn as a part of pathological myopia. We'll take it in the retina chapter, all the details. So there can be features of pathological myopia where you get retinal changes due to excessive elongation, right? So one diagram and you know what can be the findings in a myopic eye. Of course, how do you treat it? I have to give spectacles, which are mainly concave lenses, or contact lens, again concave lenses, or we can go for refractive surgeries. Refractive surgeries I'll take later. When you're using a concave lens, do you realize that it minifies your image? So all of us who are myopes, and when you wear your specs, you will realize that whatever you're seeing is little smaller, right? So please remember, for concave lens, there's minification. So when you remove your glasses, you suddenly see a little bigger. Because in a concave lens, there's minification of image. How much minification? And in convex lens, it is a magnification. And what is applying here is that every diopter, one diopter will have 2% of image size change. 2% image size change. And it will depend if there is a convex lens you are using for hypermetropia, concave for myopia, isn't it? For concave, it will minify in this. That means per diopter there is 2% minification, whereas in convex it is magnification. Okay, interesting. So this 2% has been your exam question. Another important thing is that therefore the effective power of a concave glass is more when you take it towards the eye, and for a convex it is more when you take away from the eye. Okay, so the effective power of a concave lens, effective power is going to be more in concave lenses when it is towards the eye or near the eye. Okay, when you take closer to the eye, the effective power is going to increase. And for convex, it is opposite. And how do you remember that? I'll give you a very interesting hint. I don't know whether you are these days, you new generation, are you seeing such movies or not? But at our time, there would be a Munimji who will be just using his near glasses at the tip of the nose. And he is doing all his work. Do you know why? Because his glass number has increased long back. He is not changing it. And just to adjust, he is just moving his convex lenses away till the tip of the nose. Okay, so why? Because any convex glass that you use is going to effective power is increasing when it is away from the nose. Please remember this, right? Write that also, that for a convex, this effective power is increasing when it is away from the nose. Away from the eyes, I mean to say, not nose. Away from the eyes. Please correct this. Away from the eyes. Okay? I think this is clear. These are important points we have to understand. Okay, we come to the next refractive error, and that is hypermetropia. We call it farsightedness, but again, that can cause a lot of confusion. That okay, this is mainly the problem in near vision. Aisa nahi hai. In hypermetropia, he can complain of difficulty in both near and far. So how to learn? Learn in my style. Hypermetropia is that refractive power where the required power is less, isn't it? The power in the eye, let's write like this, power in eye is less than than required. Because it is less than required, okay. Second important, eye is small instead of longer. This is smaller eye, and the light rays are focused behind the lens. Light rays are focused behind the retina. I need the focusing where? On the retina. And because I need the focusing on the retina, I have to increase the power this time. So I use convex lens. How much I should increase the power is going to be the measure of my hypermetropia. And therefore, we write it as plus. And think yourself, in your eye, there is another mechanism by which the power can keep increasing. What is that? Accommodation, isn't it? So if the power is less and you are not using specs, the eye tries its best to compensate by exerting lot of accommodation. And when the eye is exerting lot of accommodation, the ciliary muscles are working hard So the eyes get very tired and there is lot of symptoms of muscle weakness, or what do you call it? Tiredness in the eye is asthenopia. Okay. So mainly the patient of hypermetropia therefore presents not only with difficulty of far and near vision, but also with lot of headache and asthenopia. So as you can see here, the light rays are focused behind the retina. We are using convex lens. It is now focused on the retina, right? Okay, so again, how do you classify? We classify it as axial. This time it will be the small eye, smaller axial length. Second, a curvature. Again, lesser curvature means more radius of curvature, isn't it? Okay. Then next is index. How then the refractive index become less and sometimes in old age, physiological change, and positional, where there can be posterior dislocation of lens. Okay, so this time this is hypermetropia, which is axial hypermetropia, curvature hypermetropia, index hypermetropia, or positional hypermetropia. Okay, so coming back to, we're talking about what are the features, the clinical features the patient is going to complain of. As I told you again and again, blurred vision and difficulty in vision or diminished vision for both far and near. Okay. And secondly, what we learned, the patient will complain of asthenopia and headache, right? He may also have some recurrent chalazions in the eye. Again, why? Because he's rubbing his eyes to clear his image. Therefore, there can be recurrent chalazions, swellings. Okay, we come to on examination. Okay, so again, this is iris. This is your seal pars plicata, pars plana. This is the lens, the suspensory ligaments. This is the ciliary choroid, and this is your retina, right? So now what are the features for hypermetropia? Again, start thinking outside to in. So first, of course, we will write small axial length or small eye. Small eye or small axial length. Axial length is less, isn't it? Okay. And because of that, you can get a shallow instead of deep, a shallow anterior chamber. What else? There can be narrow angle. And this time the ciliary muscles are overworked. Okay, these are overworked ciliary muscles. In myopia, it was all relaxed and even got atrophied. Here it is overworked, isn't it? Right. So sometimes what happens, an overworked ciliary muscle can lead to accommodation spars. Okay. And when there is accommodation spars, this is what you call pseudomyopia. Okay. This is what we call pseudomyopia. Due to accommodation spars, suddenly the power is getting more, and this is what is pseudomyopia. Very important, okay? Another important feature, when you look at the optic disc, when you see the optic disc, we see a blurred disc margin. Though it is neither papillitis nor papilledema, you have learnt with me in neuro-ophthalmology, this is what is called pseudopapillitis or pseudopapilledema. Generally, we use the term pseudopapillitis in hypermetropia. This is also very important. Another feature, we can see some shine in the retina, and that is what is called short silk retina. Okay, short silk retina. And of course, on examination here for the lids, you can note down here, in the lids we are getting recurrent chalazion. Recurrent chalazion, especially if there is mild and uncorrected refractive error. Isn't it? Mild uncorrected refractive error. One more last point is, these patients, when they are exerting the accommodation too much, this is the story. So this is the reason you are getting pseudomyopia. This is the reason you're getting asthenopia, headaches. Okay. So one more point here. So because it is a part of near reflex, that is, what are the parts of near reflex? Whenever you're looking from far to near, there is convergence, meiosis, and accommodation. So because of that, what happens? There is convergence squint. Okay. So the story is, this is happening due to excessive accommodation. So we call it accommodative esotropia. Accommodative esotropia. This is also a very important exam question. Okay, we'll make a Q here. Accommodative esotropia. So these are the important features of hypermetropia. There's another way of classifying hypermetropia. Let's quickly see to that also. So the hypermetropia is, if it is a total hypermetropia, we divide it as latent and manifest. What do you mean by latent hypermetropia? It is nothing but ciliary body tone, and this is around 1 diopters. Okay. When you come to manifest hypermetropia, okay. So when you say manifest hypermetropia, this can be either compensated with accommodation or cannot be. So the amount of hypermetropia which can be overcome by accommodation is called facultative hypermetropia. Facultative hypermetropia is written as HF. This means it can be overcome by accommodation. Okay. And the rest of it is what is called absolute. Absolute is not, so this is mainly cannot be overcome by, this cannot be even overcome by accommodation. Cannot be overcome by accommodation. Is it okay now? Got it, all of you? So this is how you divide total into first latent and manifest. Manifest as facultative and absolute. Think with me. So what is total hypermetropia? Is when you are paralyzing the ciliary muscles and there is no factor of accommodation. So with atropine, what is the strongest convex lens which gives maximum vision? Isn't it? Which gives maximum vision. This is how we will calculate the total hypermetropia, right? Strongest convex lens where you're getting a maximum vision with atropine. Okay, so that is because we don't want to take the factor of accommodation. Then, what is manifest? Manifest means that you have not used atropine. So, everything same except this is without atropine. What is the strongest convex lens giving maximum vision without atropine? Right? So, this is your manifest. And what is absolute? How do you find absolute? So, which is the weakest convex lens which is giving the maximum vision? Okay, if you will think it's not a very difficult thing, but anyway, if you find it a little difficult, forget it. Just remember this much. Okay, nobody has asked you in that detail. So, as I told you, it's very, very important to give some extra points here. So, that is how, this is another way of classifying hypermetropia apart from the one that we did, axial, curvature, index and position. Okay, so we next talk about is treatment. The treatment of hypermetropia again will be either specs or contact lens. This time we are using convex lenses, isn't it? Or of course, if the patient is aphakic, aphakia is what? Absence of lens. What is the power of the lens? 16 to 17 diopters, isn't it? Have you learned that? Yes, power of lens 16 to 17 diopters. What is the power of your cornea? We have learned this as well as 43 to 45 diopters. Isn't it? Power of totally metropic eye, we generally take as 60 to 58 to 60 diopters. So if lens is not there, 16 to 17 diopters is less. That means it is an extreme case of hypermetropia, and we can even use IOLs to correct that aphakia. So that's why we have written here IOLs. Okay, or we can go for refractive surgeries. We are going to take that separately. Okay, so the next refractive error is astigmatism. What is astigmatism? Where is difference of refractive power between the two principal axes. Okay, so generally we consider the principal axis as 90 and 180, or you can say 180 or 0, whatever. Okay, so when there is difference of refractive power across the principal axis, what does it mean? Have a look. This is a normal cornea with both the curvatures are almost equal, vertical and horizontal, but here it is not. In this case, vertical is more than horizontal. So, if this is more curvature, one is more and one is less. It can be either way. Okay, if you want to draw, you can draw like this. Either horizontal is more than vertical, or vertical is more than horizontal, right? Anything. So, this is what is astigmatism. So, more the curvature, more is the refractive power. So, remember that. That means the curvature in this case is more here and the curvature in this case is more in the vertical axis. So, how will a patient of astigmatism look at things? If you go to the optics, the focusing should be always at the single focal point is there in an emmetropic eye or even in a simple refractive error. But when there is astigmatism, this patient, instead of seeing a letter like this, he sees it something like this. It is blurred. Why it is blurred? Because of multiple focal points. See, here there is a single focal point, but there are multiple focal points. This is the natural. Think yourself. You don't have to mug it up. When the curvatures are different, refractive power is different, focusing has to be different at different levels. That is why you get a multiple focusing points. Okay, so this is what is astigmatism. What is very important is to classify astigmatism, and let's see what are the questions asked here. Yes, so this is normal, this is astigmatic eye. So, okay, before that, how will a patient of astigmatism present? Definitely there is going to be a blurred vision and headache. Headache is due to all that eye strain. Okay, we now talk about classification, which is absolutely very important to learn and understand. So, in this case, first scenario is that you have one axis is focusing on the retina and another is in front. This is simple myopic. So, if I depict a simple myopic, one axis is on the retina means emmetropic, other axis is myopic. So, we can depict it like this. Next is your simple hypermetropic, means one axis is behind the retina, one is emmet. It could be either axis. Then we come to what is this? Both axes are in front of the retina. If this is the retina which is being depicted here. So, both axes are in front of the retina. This is your compound myopic. I will depict it as minus and minus. Then we talk about when both the axes are behind the retina. This is your compound hypermetropic. How will I depict? Something, both are plus. And if one is in front, one is behind, this is what is mixed astigmatism. One is plus, one is minus. This is what is mixed astigmatism. Right? Okay. So, we are writing either up and down because here this is not specified which one is the horizontal and vertical axis. That is the reason we are depicting in this way. Okay. Otherwise, if we know which one is which, we can mark accordingly. This is one way of classifying astigmatism. And you know, there are 4 ways. This was one way. Come to the next way. Normally, majority of the time, the axis is at 90 and 180, the two principal axes. So, the angle between them is 90 degree. This is called regular. Right? But if the two axes, the angle between the two principal axes is still 90, but they are not at 90 and 180. This is what is called oblique astigmatism. And if the angle between the two is less than 90, if it is less than 90, now you call it bi-oblique astigmatism. Okay, so this is the next way of classifying astigmatism. What is this? So, if you look at the first figure, you see this is no astigmatism. Okay, this is mainly spherical. Now, when one axis is more than the other, this is what is astigmatism. And what is irregular means, learn in this way. If I write here plus 2 and suppose I write here plus 3. When I say plus 2, it means everywhere whole axis it is plus 2. This is your regular. But what is irregular astigmatism? Even in a single axis, the number is varying. Okay? Even in a single axis, when the number is varying, this is your irregular astigmatism. Got it? So, this is what is regular and irregular astigmatism. Where have you learnt irregular? We have learnt it in keratoconus. Irregular astigmatism in keratoconus. Right. We next talk about with the rule and against the rule. If we go back to the diagram that we had drawn, let's draw it again for ourselves. If this is the cornea and suppose this axis is more curved than the horizontal. If vertical is more curved, power is more on the vertical axis and less on the horizontal. This is called with the rule. Why do you call it with the rule? I'll just explain you. And it is the opposite if suppose you can draw these, it will make your life more simple. If it is the horizontal which is more curved compared to vertical. Now, when this is more, therefore, now you call it against the rule astigmatism. So, this is ATR against the rule. This is WTR with the rule. Why are we using these terms? Let's understand. This is because even in a normal circumstance, due to the weight of your lid, there is a slight curvature in the vertical axis is more than the horizontal. Okay. So, this is the reason if this is what is getting exaggerated, we are calling it with the rule. Okay. And if it is opposite, what do you call it? Against the rule astigmatism. So, this is what we had drawn. It is here again. So, what is this? This is your with the rule where this axis is more. And this is against the rule where it is mainly the curvature of this axis is more. Done? So, we have just repeated this. If you know all this, now we come to how they are going to ask you the questions. Let's try to solve a few examples because it's very important. You should know this, how the questions are asked. The questions are mainly asked on the basis of two classifications. One is with the rule, against the rule, and second one is the same as simple myopic, simple hypermetropic, compound myopic, and so on. Okay? So, suppose, so if you take these two classifications, I give you first question. I say, this is, tell me, what type of astigmatism is this? According to these two classifications, what will I say? It is a compound myopic. Is it with the rule or against the rule? Now, this is what you have to think. When I say -2, I mean to indicate here is, there is myopia. Minus is myopia. Myopia is more power. -2 का मतलब क्या हुआ? What is the power of a emmetropic eye? 60. So, -2 का मतलब actual power here is 60 plus 2. And actual power here is 60 plus 3. So, when you write minus, actually you have to add to the emmetropic power. Which is more? Definitely, this is against the rule astigmatism because the horizontal curvature has more power. Easy? Okay, let's see the next example. Now I say this is +2 and +3. Think again with me. This is now compound hypermetropic. Now which power is more? +2. Plus is hypermetropia. Whenever you are saying +2, what is the actual number? 60 minus 2. When you say +3, it means what? 60 minus 3. So, this is what? With the rule astigmatism. So, here the power is more, +2 is more power than +3. I hope I am clear. I explained you how the hypermetropia is mainly indicated with the plus. So, on a retinoscopy, if you write plus and minus, it is mainly go ahead, don't use your algebra at this point, just understand minus is myopia and plus is hypermetropia. Okay? Okay, let me come to the next example. Now, all of you, what is this? How you classify? I'll classify it as simple myopic. Which one is more power? This is 60 diopters, this is 60 plus 3. Agreed? So, this will be with the rule astigmatism. Okay. Next example. Next example is, this time I say this. Now, what is more power? More power, this is simple hypermetropic. More power is 60. This is 60 minus 2 because it is hypermetropia. Therefore, it is more power is at the vertical. So, this is with the rule astigmatism. Right? Okay. What about this one? Can you all answer me this? What type of astigmatism is it? Compound myopic. And what type of astigmatism is this? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Answer me. This is not astigmatism. The two numbers are same, okay? So here you will answer no astigmatism. Okay? Interesting? Good. Okay, so we'll come to the prescription later on when I discuss retinoscopy, and then I'll discuss again with you all. Let's come to the next thing. How do you treat your astigmatism? Of course, we use cylindrical spectacles. Cylinder lenses will give number only in one axis, so astigmatism is treated with that way. For contact lens, we use toric contact lens, and we can go for refractive surgeries, right? Okay. Next we talk about is, what is anisometropia? Anisometropia is an important exam question where the difference between the two eyes is more than 2.5 diopters, right? This is what is anisometropia. And lastly, what was the next refractive error? Anisoconia. This is difference of image size, okay? So when there is a difference in the image size, so all of you, do you all know that 5% of the difference is physiological? And this 5% of difference is going to help us in depth perception. So all of us who have a 3D vision, this is helping in depth perception. But if it is more than that 5% physiological value, now you call it anisoconia. Got it? How do you measure it? By just know the name of the instrument is a echinometer. And how do you treat? We use isoconic glasses. ये क्या होते हैं? What are these glasses? Isoconic glasses. So what happens? These are nothing but magnifying glasses, just to make the two images equal. That is why you call it isoconic glasses. This is all you have to know about anisoconia. So these are the refractive errors. Next we talk about is what is aphakia. Okay, so aphakia is what? Aphakia is absence of lens. So when you say absence of lens, what is the refractive power of the lens? क्या पढ़ा था हमने? Refractive power of lens is around 16 to 17 diopters, isn't it? So we are saying that there is 16 to 17 diopters less in the eye. And what is less power? Hypermetropia. So I think we can understand this, that what is aphakia? It is high hypermetropia. Hypermetropia. No? Got it, all of you? 16 to 17 diopters is less. When it is less, this is a case of high hypermetropia, less power in the eye. So this is mainly, you have to first understand this. About how will the patient present? A high hypermetropia patient, clinical features. Of course, he will have a difficulty in vision, both for far and near. Right? And what are the on-examination findings? Let us make a diagram and learn the on-examination findings. What are the on-examination findings? So, this is your eye, there is no lens, this is your ciliary body, this is your choroid and retina. Okay, first important thing, let's understand that the total refractive power, because we are decreasing by 16 to 17 diopters, the total refractive power will be how much? Around 44 diopters. Second important feature, deep anterior chamber. Because there is no lens, we have a deep anterior chamber. And this also means no suspensory ligaments, no lens means no accommodation. Okay, there is no accommodation. Another important point, so you understand the nodal point concept which I taught you, how the parallel rays of light focusing by the cornea, by the lens is focused behind the lens, and that point is the nodal point. Now there is no lens, so that focusing will happen so the nodal point actually moves forward. Just remember, nodal point will move forward. Moves forward. What is the exact location of the nodal point in a normal emmetropic eye? You should know this. Nodal point is 7.08 millimeters away from the anterior surface of the cornea. So actually, normally if I talk about the normal situation, the nodal point is 7.08, okay? It is 7.08 mm from anterior corneal surface, right? Okay, and then what about the iris? Can you think something about the iris? Yes, there is no support of the lens, so we will learn here iridodonesis. Iridodonesis. So once you know the features of the aphakia, now we talk about the treatment of aphakia. So treatment can be either specs, it can be contact lens or intraocular lens. First question is, and of course refractive surgeries, some refractive surgeries are there to treat high hypermetropia. We'll talk about it in the refractive surgery section. Coming to what is the treatment of choice, what you should answer? We will always answer treatment of choice is intraocular lens. Another question, what is the choice of site of IOL implantation? What is the choice of site of IOL implantation? What will you answer? It is capsular bag, in the capsular bag, or you can say posterior chamber or capsular bag, right? Okay, next question. Next question is, sometimes they have also asked you about which is a drug. I'm going out of the way here, but suddenly I remember this at this point, so let's just discuss this with you. It's a pharma question. Which drug has only mediatric action with no cycloplegic action? So what will you answer? It is only mediatric is only one drug. So remember, all mediatrics are cycloplegics except one, and that is your phenylephrine, right? So we'll remember phenylephrine. And which is the strongest cycloplegic? Of course, we all know this. It is atropine. So strongest cycloplegic, if they ask you, they have asked you all these questions. Okay, see, I'm making a cue here. So we answer atropine. Anyway, let's move further. If you are treating the aphakia with specs, do you realize that for 16 to 17 diopters to be compensated, the specs or the convex lens that I am going to use has to be plus 10 to plus 14 diopters, right? Now, this is very high and thick convex lenses. If the patient is using the specs, now the problems which he will face is through specs, not due to aphakia. So, if he is corrected by these specs which are plus 10 to plus 14, he has few challenges to face. What are those? So, first would be high magnification. Okay. So, first important point, this patient is going to face will be the one problem is due to the high number of the convex lens, because we have learned this. Convex lens magnifies the image, concave lens minifies the image. How much? We have discussed this earlier as well, that one diopter corresponds to 2% change in the image size. So here this is high because just imagine the amount of diopters. So very high magnification and therefore of around 25 to 30%. Okay. And this is what you have to understand. If you are using a high convex FAK glasses, magnification is very high. Now keep thinking with me, if magnification is very high, what are the repercussions? If this patient has aphakia in only one eye, suppose he was a case of trauma. Think with me, one eye is 25 to 30% more than the other. This is too much of difference of image size. That means any uniocular aphakia, keep writing as well, for uniocular aphakia, what is happening? This is leading to high aniseikonia. And such a high aniseikonia means what? How much can you tolerate? Only 5%. Any difference of more than 5% is aniseikonia, and too much of aniseikonia means the two images cannot merge. The difference of size is too much. And if the images of the two eyes cannot merge, what will happen? Double image. So what you get here is diplopia. Okay. So this is one problem. High magnification can lead to high aniseikonia if the patient has aphakia in only one eye. Therefore, we cannot treat a uniocular aphakia with specs. So, for uniocular aphakia, please cannot treat with specs because of high aniseikonia leading to diplopia. Okay. Then, of course, these aberrations like spherical aberration, chromatic aberration, and your pincushion effect, which is caused due to spherical aberration, all these can be seen in the optical system. And if you're using a higher the number, higher the aberrations. Just understand this way, that all these aberrations we are talking about, if you talk about the aberrations in the optical system, apart from magnification change, pincushion effect is due to high spherical aberration, hai na? And then chromatic aberrations, high prismatic effect. So all these aberrations are present in the lenses, whether we are talking about convex or concave. Just remember, more the number, more the aberration. Okay, so we take one by one. High magnification you have understood. With second is high spherical aberration. So if you have a look and you go back to your physics a little bit, if you revise, so if this is the prism and the light is, this is the refracted light from the prism, right? It is moving towards the base, right? Light goes towards the base and image shifts towards the apex. Remember this. Now what is happening here when you see this is a concave lens, a minus lens? So a minus lens is nothing but combination of two prisms apex to apex. This gives rise to minus lens. Understood? And when the base to base is attached, you get a convex lens. When this is a plus lens where base to base prism is attached, right? So you know already that when you say concave, the concave is going to diverge the light, right? And convex is going to, so this is diverging the light here, and when you draw it back, trace it back, this becomes the focal point, isn't it? You have learned all this. Whereas in a convex lens, this is the focus point, focal point. Anyway, this was just a quick revision. You will be thinking why ma'am is teaching this, because if your basics are clear, you understand better. Anyway, if you know this, what I was just trying to tell you is that all these aberrations can be applying to both these lenses, and more the number, more are the aberrations. Okay, coming to what is spherical aberration. So if you look, what is a spherical aberration means that the periphery of the lens, at the periphery, this is your light rays, and this is the optical axis shown here, and this is the best focal point. So can you see from the periphery, the bending is more than from the center, right? So this is what is spherical aberration, when the bending from the periphery is more, bending at periphery is more, refraction of bending is more. So what happens? When the strength of that lens is more number of the convex lens, so this bending will be more. So more the number, more the aberration, right? So if the spherical aberration, I'm saying, is due to more bending at the periphery, this is a normal phenomenon. But if the number is more, it is causing more problems, right? What is the problem the patient faces? Because there is too much of bending from the periphery due to the high number, everything the patient sees is curved. It's a parabola. Even if he is looking at a tube light, it is not straight, it is a parabola. This is what is called pin cushion effect. So if he is using, suppose this was a normal square, right? So this was a normal square, so everything is curved for him in this way. In this case, it is like this in a convex lens, and this is what is called, if he is using a convex lens, this is the distortion. This is what is called pin cushion effect. Okay? So pin cushion effect is due to high spherical aberration. Correct? Okay, we come to the next. Look at this one. This is normal, right? This is an undistorted square pattern. This one is your pin cushion effect due to the convex lenses. But if the patient is using concave, I told you both type of lenses will cause the aberration. For convex, this concave, it is a barrel effect. So this becomes a barrel distortion in a concave lens. And here in a convex, it is a pin cushion effect. So this patient of aphakia who is using such high convex number in his specs will face a problem of pin cushion effect due to high spherical aberration. I think now it's clear. So come to the next one. What is chromatic aberration? Chromatic aberration means that longer wavelength, like if you look at the chromatic aberration here, what do you see? That longer wavelength, lesser the bending. So the red is bending lesser compared to the blue, which is bending more. Shorter wavelength, more bending. Again, this can lead to some chromatic aberrations. More the number, more the aberrations, just keep this in mind. So this may trouble the patient if he uses more and more higher numbers. So you have just understood how apex to apex alignment gives a concave lens and this gives a convex. So whenever you're cutting the lens and you're forming the spectacle lenses, right? What happens is, periphery of every glass has prismatic effect. Just remember. Okay. So periphery of every glass has prismatic effect. That means he cannot see from there very clearly. Understand more. If you have gone for your spec to get your specs made, do you realize we generally see the optical center of your eye? We match it with the glass. Okay, this is it. Why? Because if you just take out your glass, try to see from the side of the glass. you will see you can't see clear. You see more clear at the center than the side. Why? Because of that prismatic effect. Okay, so every spectacle, concave or convex, will have the prismatic effect at the periphery due to the cutting of the glass like that. Now what happens? That means from the periphery you will not see clearly. Now when the patient here of aphakia is using the number, he is using very high convex lens. Kitna high? Very high convex lens means plus 10 to plus 14, that's what we read. So with such a high, the prismatic effect is too much. So much so, nothing is seen through the periphery, right? So if he takes his phakic glass and try to look, of course, it is very bad. You can't see. So that is what you have to learn. High prismatic effect, nothing is seen. When nothing is seen, it's a scotoma. And if this is a scotoma, it is all around your eyes due to the periphery of the specs. This is what is called ring scotoma. Keep listening. And this ring scotoma, suppose these are phakic glasses, when my head is moving, will move around. The glass is moving around with me, so the scotoma is moving along. So this is why we call it roving ring scotoma. Okay? So the roving ring scotoma. So this roving ring scotoma, can have a look, because of that high prismatic effect of your, so you can just understand here, this is your high prismatic effect, which is going to lead to this type of, the field is all cut, you know, almost like a constricted visual field because of this roving ring scotoma, right? Now, if suppose this patient has to see, is looking at, so two people are sitting in front of him and he wants to focus on both of, he is not able to. Once he is looking at one person, the other is out of his sight. When he looks at the other one, the first one is out of the sight. Now this one is out of the sight. Because of that constricted visual field, which because of this ring scotoma, roving ring scotoma, you got it? And this getting out of the sight is what we call Jack-in-the-Box phenomenon. So Jack-in-Box is generally a game, but you should just know this. What is Jack-in-Box phenomenon? Is when he is looking at one direction, he can't see the other one. When he looks at the other direction, he can't see the first one. So this is happening due to roving ring scotoma. This should be absolutely clear to you all, and this roving ring scotoma is due to high prismatic effect of a thick lens. Due to high prismatic effect, okay, of a thick lens. Okay? Okay. So if we are clear with this, then we also understand this, that if there is no lens, there is no accommodation, so we have to use near glasses. Okay, so once there is no aphakia or in pseudophakia, when there is no lens, we understand there is no accommodation. So you need near glasses unless and until in adults you are using a multifocal IOL. So this was the exam question when you talk about pediatric aphakia or pseudophakia. Okay? What glasses the child will wear. So do you realize something? If you are an adult, you can decide, okay, I am doing a near work, I will use my near glasses. But in a child, the child cannot decide, na, that okay, now I am looking at the near, let me put on the glasses. So he has to be given a glass which he can wear continuously, which is taking care both for his far and near. Even if he has no number in the far, it has to be taken care for the near. So what we use is executive bifocals. Okay? When you talk about bifocals, this can be of three. One whole division like this, and I hope you have this idea. Suppose the distance is in this patient is -1 diopter spherical. Okay, so if I am talking about -1 diopter spherical and he has a near of +3, suppose you have to give, or +2 you have to give. So how do you decide? We add. So it has to be added to this. So when you add the near, it means -2 plus -1 plus 2. Okay. So this you have to know that this will become +1 diopter spherical for the near. So the near is always added to the far value. So suppose I say it is the distance is +1 and I am also giving +1 for the near. So actually in the near, the total would be +2 diopter spherical. Now you got it? We add the near to the far. Okay. So this is how you generally give a bifocal or near glasses. These are the shapes you can cut the lens into, either circular for the near or this one, or when you are dividing it equally, this is what is called executive bifocals. And this is preferred for small children. Executive bifocals, preferably. Now, of course, what we are using is, we are also using progressive glasses, which takes care of not only near but intermediate and far distance, isn't it? Yeah. So these are the executive bifocals. Actually, this was given in your exam and they had asked you about pediatric aphakia, which glass you're using and what it is called. This is your executive bifocal. This is what it is called, because you can see the division is all throughout like this, right? So now is it clear? This is for the near and this is for the far. Next we talk about is accommodation. Okay, a very quick revision here. What we had learned, what is accommodation? When the patient is looking from far to near, what are the three things happening in his eyes? Convergence, meiosis and accommodation. We have already learned, I will quickly revise here, that accommodation has three main steps. First is your contraction of ciliary muscles, and when the ciliary muscles are contracting, what is happening is relaxation of zonules, and when these zonules they relax, there is mild increase in curvature of the lens, right? And more the curvature, more is the power, so there is increase in refractive power which you need to look at the near. This is number 3 and this is 1, 2, 3. These are the steps of accommodation. Clear? Okay. When you're talking about accommodation, next thing, an optics point of view, and of course, when you're talking about accommodation, we also know this, that after the age of 40 years, what happens? After the age of 40, your ciliary muscles are weak. We have learned this. Lens becomes more rigid. So, now when you're looking from far to near, the increase of curvature is not happening so smoothly. So, this is what is error of accommodation, not refraction. And this error of accommodation is what is called presbyopia. So, this is what? This is error of accommodation. This is called presbyopia. So, when you say presbyopia, it means this time the power is not being able to increase for the near. If the power is not able to increase for the near, how will you manage it? Whenever there is less power, you give convex lens. How is it different from hypermetropia? Because this time this convex lens I will give only for near. Therefore, we call them near glasses or presbyopic glasses. Near glasses only for near, okay? That is presbyopic glasses. Okay, if we are clear with this, next important thing. Next thing they ask you, of course, this presbyopia generally in emetropic eye, this presbyopia is going to set in by 40 years. Plus minus 1 year, but generally 40 years. Some people, there may be some physiological change, but we have to learn this. Now, the question was, if your patient is already hypermetropic, will this presbyopia set in early or late? And if your patient is myopic, will it set early or late? Think with me. Hypermetropia is already less power. Presbyopia, again a problem of less power for near. Therefore, if the patient is hypermetropic, it sets in before 40 years. Got it? Because there is already less power. And when we talk about myopia, it's already more power, M for M. So, more power in myopia means this time it is after 40 years. So, after 40 years, it will take time to set in, okay, because the power is already more. So, this is one important point that you have to remember. Secondly, we all know when the patient is at the age of 40 years, you are giving how much of correction? Generally 1 diopters. He becomes 45, you give 1.25 and so on. So, it is age wise we can learn or we can predict, if of course this is only possible if the patient is having only near with no far correction. Because as you can see, if he is already hypermetropic or myopic, it will change. But for an emetropic, what is the prediction according to the age? Very simple. I've taken 40, then 45, 50, 55 and 60. So, learn like this: 40 years, 1 diopters, right? Then 45 years, it goes to, of course, it goes to 1.5 diopters. Yes, not 1.25, but 1.5 diopters. Then 50 years, it becomes 2 diopters. So, write like this, you will learn. 55, now it is 2.25 diopters. And when you say 60, it is plus 2.5 diopters. Right? So, this is how we can judge. So, this was also your exam question, that your patient is of this age. What correction do you expect? So, please have this idea. Right? This is all interval of 5 I've taken to make things simple for you all. The third question on presbyopia is, what are the causes of frequent change of presbyopic glasses? So, this is another question on presbyopia, frequent change of presbyopic glasses. So, the near number is changing again and again. What can be the cause? 3 main causes we will learn. First is early cataract. Now, I generally teach like this. Why? I'll tell you. Early cataract, late glaucoma, or diabetes. This is how we will learn. Okay. So, we don't say diabetic cataract. Please be careful. We are saying early cataract because it is the intumescent cataract where if the water is more, swelling is more, then it is a myopic shift. I need lesser number in my near glasses. If the swelling is less, now I need more number in my near glasses. So, it keeps changing. So, we are talking about intumescent cataract where the water content is changing and therefore the curvature of lens is changing. So, late glaucoma means this is generally factual. Late stage of primary open angle glaucoma can present with frequent change of presbyopic glasses. Coming to diabetes. Diabetes, actually everything varies on the blood sugar level. If this patient is hyperglycemic, more sugar. If the patient is hyperglycemic or more sugar, what do you see? There will be more sugar means more swelling, more in the lens, and therefore there is myopic shift. So, this has been your exam question, that in hyperglycemia we get a myopic shift, and when there is hypoglycemia we get a hypermetropic shift. Right? So, do you all realize this is the reason if my patient is a diabetic, I should see his blood sugar should be in normal levels, then only I should do the refraction. Otherwise, he is going to very quickly come back to me for this refractive correction again. And of course, he is not going to be very happy with me as well. Right? Okay. Then another thing, why early cataract we teach? Because there was a question. Frequent change of presbyopic glasses is an early symptom of cataract, glaucoma, diabetes. Early symptom, therefore you answer cataract. Okay? Got it? Why I am teaching like this? So, early cataract, late glaucoma and diabetes. Okay, then we should have a very clear concept about what is far point and what is near point. Far point is punctum remotum. Near is punctum proximum. So, what is far point? Is the farthest point where we can see clearly. As simple as this. What is near point? Nearest point where you can see most clear. This is your near point. So, far point for an emmetropic eye, I hope you all are very, very clear that if you say emmetropic eye, it is infinity, right? If you talk about far point in a myope, of course, is in front of the eye, in front of eye. And if we talk about far point in hypermetrope, this is behind the eye. For a hypermetrope, this is behind the eye. Just keep this in mind, it's very important. Okay, then we talk about the near point. Of course, the nearest point where you can see clearly means there the accommodation is exerted maximum. Okay, so we have to keep in mind there's a maximum accommodation in force. Right? Okay. If we are clear with what is near point and far point, do we realize that the distance between the two is what is called range of accommodation? And the difference of power between the two, the power exerted at the near would be the maximum, at the far point it will be the minimum, and this is what is called amplitude of accommodation. Okay. So, this is range of accommodation is what? A is the range is generally small a is R minus P, remotum minus proximum. What is the distance from far point to near point? Remotum and proximum. And when you talk about the amplitude, we use a capital letter as a nomenclature here. So, amplitude of accommodation would be, of course, power at the far point, proximum minus remotum. This is important, you should know, because there are some numericals that are asked in your exam. Okay? Okay. So let's solve a few numericals here. First is, with a near point of 20 centimeters, a hypermetro plus 4 has to exercise accommodation of. See, for all these numericals which are around this near point and far point, two tips very, very important. One, we have to remember that par is inverse of focal length. Sorry, par is this you have learned, par is equal to inverse of focal length in meters. And of course, second is your A is equal to P minus R. You just learnt with me, that is power at the proxima minus power at the remoter. And of course, the third point that we have to keep in mind, that the far point for hypermetrope is behind the eye and for myope it is in front of the eye. Now let's solve it. When you say the near point of 20 centimeter, it means what is the power at the near point? Power is 1 upon 20 in meters, so it becomes this, right? So when you say this, what is the power? It is mainly, what is the power here? It is 5 diopters. Okay? So 5 diopters is the power P value. It is 5. Correct? He is asking you what is the amount of accommodation exercise. That means the question is about the amplitude of accommodation. He is a hypermetrope of plus 4, means at far point the power is plus 4. Now pay attention. So R is equal to plus 4? No. The hypermetrope of plus 4, of course, when there is a hypermetropia, we write it as plus. We have discussed this. He is a hypermetrope of plus 4, means that the diopter, that the power at the far point is indicated as 4. But because the far point is behind the eye, the light rays are focused behind the retina. Therefore, it is indicated in a minus sign. So, actually it is minus 4. Okay, so plus has been given because it's a hypermetrope. But when we are solving the question, this is the only trick you have to keep in mind. कि अगर the patient is hypermetrope, we will use a minus sign here. Minus minus becomes plus. You have to use your algebra now. So this is the answer. So answer becomes 9 diopters. Okay. So hypermetrope will be exerting how much? It is 9 diopters. Is it clear? Had this patient not been a hypermetrope, I would have said 5 minus 4. Okay. Yeah. We come to the next question. With a near point of an emetropic person, what is the near point of an emetropic person with an amplitude of accommodation being 7 diopters? Let's solve this. So let's solve this one. What is the near point of an emetropic person with an amplitude of accommodation being 7 diopters? We go back to our same formulas. So, if amplitude of accommodation is equal to power at the near minus power at the far. So, this is 7 diopters is equal to power at near minus what will be the power at the far? He is emetropic. What is the far point of emetropic? Infinity. So, what will be the power? Because the far point is infinity, power is 0. Okay. So, here the power is 0. So, that means the near point power is equal to 7 diopters. Okay? But what is the question? They are asking you the near point. So, you have to tell the distance. So, how do you calculate that? We all know that power is equal to 1 upon focal length in meters. Right? So, let's see this. It will become, yeah. So, power is how much? This is 7 diopters. So, 1 upon focal length in meters. So, you have to convert it. So, it becomes 100 upon 7, which will be around 14.2 centimeters. Right? Clear all of you? Okay. So, be very, very alert what the question is. Are they asking you the power or they are asking you the distance, that is the near point or far point. Okay. So, this is how we are going to solve these questions, right? So, what is this? Have a look. Which instrument is this? This is your RAF ruler. RAF ruler stands for Royal Air Force. Mainly it is used to see the near point of convergence and the near point of accommodation. So, if you look here, the patient's, this is where it is fitted on the nose of the patient, right? Like this, he will keep at this end, he fixes on the nose and this box is being moved. Okay. Now, you take it nearer to your eye, and the point where this becomes blurred is the near point. When there is blurring, that is your near point of accommodation, and the point where there is double vision becomes the near point of convergence. Just remember this, okay? So be familiar with this instrument, sometimes they can ask you.